All right. So, originally I wasn't like planning to tell you about my trip to um, British or in general Scottish, Scotland, right? Scotland. But anyway, so but how many of you know that why are we calling ourselves Highlanders? Or any of you are aware of UCR Highlanders? Okay, you know that, right? Right. Okay, so if you are aware, the mascot of our school is a Scotty Bear, right? And why is it a Scotty Bear? Because it's a Scotland. Um, and the reason, and if you are ever aware of any of the like NCAA sports events at this school, you will figure that out. We call ourselves Highlanders. Every school has their own names. Like at UC San Diego, we call ourselves Tridents, right? And here we call ourselves Highlanders, right? And if it's Stanford, trees. I'm not kidding you. And and like MIT, beavers. And I ever ask them, why are you calling yourself beavers? Because they say those are the engineers inside the river. That's MIT. A very good one for them, right? And what else? Oh yeah, Berkeley Bears, right? Like UCLA Bruins, right? So we are Highlanders. And the reason why we are calling ourselves Highlanders, because the elevation of UCR is actually the highest among OUC campuses. So that's why we call ourselves Highlanders. And in UK, the like tallest place is actually in Scotland. So that's why they are. That's why UCR tried to imitate the atmosphere of Scotland. So if you pay attention to all the residential colleges or residential halls, they all have a Scotland name. So for example, like Glasgow, that's the largest city in Scotland. And I don't know if we have any building named after Edinburgh, which is which is the place where I just traveled back from. But next to Glasgow, there is next to Edinburgh, the surrounding area is called Lothian, right? So some of you might already know where Lothian is, right? So there is also a city in Scotland called Dundee, right? So if you often go to those dining halls, you are probably aware of those. Okay, so originally I don't plan to talk about my trip, but some of you asked me about that question yesterday, so I prepared some slides. So I personally think it's a little bit unfortunate because I have to come back and teach you guys. Otherwise, I should stay longer. Okay, so I'm only there for like 41 hours, but I already love that city. So this is one of the city view of Edinburgh. So you can see like it's a very classical view, and everywhere in that city. And this is their old castle, and I actually like purchased the ticket to go into the castle. A lot of place you cannot take photos with, but for this one, I think I only saw this in a movie, but this is the first time I see it in person, and they are really the historical ones, and they are preserved very well. And this is the city. That's the downtown of Edinburgh, right? So you can see it's like maintained in a way very classical, right? And sometimes when I walk in that city, I'm feeling like, okay, UCR, we call ourselves Highlanders. We kind of like saying that we are imitating the atmosphere of Scotland. We should actually make our building look like this, right? Then we will probably become one of the tourist places in Southern California. But anyway, so sometimes when you go to like sightseeing with some places, right, you're definitely thinking about like what kind of souvenir you should buy. And sometimes, and before my departure, I was talking with my roommate, okay, what should I buy? And we don't actually think about we actually cannot think of anything on top of my head at that time. But then when I arrived at Heathrow Airport, I just figured out, oh yeah, Harry Potter, that's something from UK, right? But I walk around, okay, very expensive, so I give that up. And another thing, when I arrive at Edinburgh, I just figure out, oh, Johnny Walker whiskey, right? So actually, I bought one, but because this is the campus, so I cannot bring any alcohol by default, right? So I didn't bring it here, and even though I have one, I cannot tell you. And another thing, so typically on YouTube, we mark our video to be like made for kids, but definitely not today. So the thing is that, okay, it's kind of interesting. I found this. So this is like a vending machine in the male's restroom. And I don't know why they put this there, but apparently they remind me there's another brand, like worldwide brand is from England, right? That's, yeah, right? Although I still feel very strange. Why are they putting this in a men's restaurant? Restroom, right? Like a restroom, right? Why restroom? Okay. Anyway, all right. So, but before we start talking about our main topic today, right? So, a few things. So, first of all, we have been talking about how to improve the performance of the system in several different ways. So, first of all, if it's very compute intensive program and we found CPU performance is not satisfying, we should try to seek for other help, for example, hardware accelerators. And sometimes if it's a memory bound problem, we should think about, can we do near data processing in memory or in storage? However, depending on where your data location is and how dependent are you on the computing, sometimes these approaches may not be working, right? And then we talk about, well, something that we oftentimes ignore. For example, like the data formats actually matters. So, and one of the examples that I gave you is that, okay, if we combine all things that we learn together, we are actually able to create some kind of in-storage processing unit that would actually help us to speed up or say improve, well, not speed up, but improve the overall performance of the end-to-end latency of an application. So for example, in Morpheus, which is one of the paper that I wrote before, we try to create application objects directly inside the storage device and then send it out so that we can reduce the traffic and make the end-to-end latency better. And also, like, data formats matters, right? So we have been talking about there are different popular formats, but they are far from ideal. And one of the proposal is Albus. So one thing it does is that, okay, instead of just dividing your data by row groups, we add both row groups and column groups. And in fact, why this works is because it better fits the application demand. So here are a few things that we hear, right? Like application demand matters. How application use your data matters. And what kind of data formats would better support your application matters, right? However, in the past, why our system design doesn't really take care of this application demands. And one of the reasons is because we are so well, the computer industry, or say the computer engineering industry, is so well structured based on the layering design. So typically, when we say layering, right, it means that, okay, we create boundaries among different parts of our computer system. And if you are an engineer working on a certain project, certain part of your whole system, we typically ask others, don't cross my boundary, right? Don't cross the boundary, right? So turns out this is what our world looks like today. So for example, if I am a machine learning engineer or a so-called data scientist, what I typically would know is just like programming language at a very high level, like Python, Perl, okay, nobody uses Perl now, R, or any kind of like very high level language, right? And well, and a lot of us, and also Java, right? That's also a very high level language. Well, C or C++ programmers, they are better because they are closer to, they have to know more about the hardware. But other than those, right? software engineers or data scientists in general, we are living in a very well-structured world that we only program at the level of abstraction provided by the programming language framework. However, we don't care about anything else. And the reason why in the past we don't care about anything else because we trust the underlying infrastructure, for example, the CUDA, TensorFlow, PyTorch, or all the libraries can help us address those issues. So we believe as long as I know use the function code of them and compose programs based on this stuff, then I'm good enough. I don't have to worry about all the rest of things, right? And underlying, you have architecture, you have operating system like Linux, Mac OS, or Windows, Android. They all do their own stuff to make sure that the system is well isolating from process to process and ensure the utilization of all the underlying hardware. So that's the job of operating systems. And again, when I am optimizing my PyTorch or TensorFlow or cuDNN framework, I don't actually take care what the underlying operating systems are doing, right? So because we thought that's a different layer stuff. And at a hardware level, we just think, well, we just receive all what other people are giving me. And then I'm trying to optimize those operations at the very fine-grained basis. For example, I'm optimizing for my multiplication, I'm optimizing measures multiplication, I'm optimizing those like fine-grained commands that people might give me. So that's the layering approach, has been leveraged since the very beginning of computer engineering industry, computer science in general, right? So now, I want you to think about what's wrong with it, or is it still good, right? Like, what are the good things about this kind of approach, and what are the bad things about this kind of approach? So let's go ahead and grab a few ones around you and discussing why is this a good approach, or why not this is a good approach.
when you started this one project, was just my online project. I leave keep your walk away from my and turn to almost do it for us. Like he calls me up, he's like, I know your contract's ending in 3 months. I don't offer to buy your contract.
All right. You guys are talking about contract. So what do you guys think about layering design?
I think it's good.
It's good?
Yeah.
Okay, in what way?
It's easier to program, and you don't really have to have too much low-level knowledge.
Okay, so it makes program easier, right? So ease of programming. What else? Oblivious to each other. So what does that mean? Each layer doesn't really have to know about other layers. It's pretty much like what we do, right? So in general, it makes programming easier, right? Programming easier. What else? Who knows what's the original purpose of layering? What? Yeah. From networking? Are you sure? Do you know what's the earliest paper talking about layering design? Do you know who wrote the very first paper about the layering design ever in computer science industry? What? Not me. No, I'm not that old. I hope I'm the person. You must heard about his name. Peterson, no. He's not old enough. So that the first people who, I think it was a paper in 1969. You guys know? Yeah, exactly. The Dijkstra paper, the THE paper, right? So it's very interesting. THE paper presented as an operating system paper, but it actually has a strong influence in software engineering because, and who remember what was the original purpose Dijkstra talking about layering? And why software engineering adopt that? What? Find the shortest path? Okay, that's not the THE paper. So THE is really a great paper, and if you don't remember what THE paper about, you should definitely go back and read it. So, so layering is just one thing, and the other thing is mutual exclusive. Like that's another contribution of that paper. But surprisingly, that algorithm is actually in the appendix of that paper, right? So that's not even the main topic of the paper. The main topic of the paper is actually talking about the layering design. But why layering design? And another ironic thing is that after Dijkstra paper, there's no paper using the layering design. So apparently, layering design has its own bad part about this idea. So what's that bad part?
But I guess it'd be like control, because if you can't control what the other layer is doing, it could be messing up when you tell it to do this, but somehow in its internal logic, it has a structure where it doesn't really do it that good.
Yeah, right. Isn't that like real life? Right? You thought, well, every layer should work on their own and they have local optimization, right? But they have different optimization target, right? So for example, like, okay, your advisor may want you to optimize for the amount of work that you can do, but maybe you are optimizing your life in the amount of good food you can eat, the amount of trip you can make, right? The amount of skis that you can like ski resort that you are going to, because one of my students, he really he bought a ticket like every Thursday. He's like, okay, can I leave earlier today because I'm going to like Utah or somewhere else, right? So, right, like different target of optimization, right? So, okay, so every layer has its own target of optimization, and those targets may against each other, right? So that would potentially lead to what? Slow down, right? So it may be slower. And even though everyone is optimizing for the same goal, is layering a good design in terms of performance? Not really, right? Because every layer has their own overhead, right? Like memory copy is one of them, right? You learn this in networking. All right, so those are the bad parts. But regarding the good parts, I haven't heard any of you talking about what was the original benefit that Dijkstra talking about, right? Because, I mean, Dijkstra is not an idiot, right? He knows there would be an issue in performance. But there is a strong reason why he wants the layering design. And that's actually the strong reason why software engineering and networking, or even the PCIe interconnect, they take this design approach. What is that?
Would it be modularity?
Modularity. Okay. What's the good thing about modularity?
You can take different systems together
You can take different systems together
and make it so that they all can work together without having to implement specific architecture.
Okay, so here is an interesting thing, right? Modularity and layering, they are two different concepts. And modularity, so for example, they can all be at the same layer, but you can have different plugins as a module in the same layer, right? But they are just like individual elements, components in your big project. So that's actually a different concept than layering, right? Like modular, they don't have to be vertical. They could be horizontal, right? So regarding layering, right, it's vertical, right? So what's the reason why for the layering? Portability? Tell us more about it.
So let's say we implement 6 layers of some software.
Mm-hmm.
And only the last layer is architecture specific.
Mm-hmm.
We can implement just that last layer for another architecture, and we can just move this.
Okay, so you can swap in and out one of the layers as long as
the APIs are different.
So the thing is that, okay, if you have layers, right, and if and you're kind of like abstracting each layer on its own, right? So as long as their abstractions are compatible with each other, you can swap in and out. Okay, closer, but not actually the original purpose of the THE design. What was that? Do you guys read that paper in 202 nowadays? No? How come? Okay, I have to talk to your teachers in 202. What was that? What's the main reason? What? Testing independently. Okay, so close. Almost there. Okay, so each layer can be testing independently. But what's the point of testing independently? Debugging, you got it. Okay, so programming is not that easy, right? How much time you spend in debugging versus developing? 90% of the time in debugging, right? So actually debugging is the most time-consuming thing in programming. Trust me, right? Like I can find bugs in almost every program, right? Every program has a bug. Every program has a bug. No matter, well, I mean, originally I thought it's just logic flow, right? A lot of you were working on security, so now we have security bugs. And when we want to run the program in parallel, there is concurrency bugs, right? So there are bugs everywhere. So why Dijkstra proposed the idea of layering? The fundamental reason is that, okay, engineers work on this layer as long as this abstraction, this interface is defined, right? And I can easily figure out which layer gets wrong, right? I can easily figure out whose fault in making this project failed by doing this unit testing, by testing each individual module in the layer separately. I can figure out which layer is wrong. And also, the strong implication in computer engineering or in networking in general, right? Especially in networking, every layer has a different company that's dominating, right? So for example, in a physical layer, right, there are antenna companies. They want to control their own stuff, right? And in a Mac layer, right, there is companies like Qualcomm. They dominate the LTE 5G, and there is Broadcom. They dominate the Wi-Fi, Bluetooth, right? And at the networking layer, there is like Cisco, Huawei, this kind of company. They produce a lot of routers, right? And at the TCP/IP level and or application layers, you can see different vendors. They are doing different things, right? So it also allows like each different companies to collaborate and easier to work with each other, right? And because of that, right, I can, as some of you said, well, today I don't really need to use a Cisco router if I have Huawei provide cheaper options, right? Or today I can easily switch my protocol from Wi-Fi to Bluetooth without rewriting my application, right? So those are the benefits of having layering. However, the bad thing about layering is performance, right? Because every time, like when we cross different layers, we have performance loss because of the memory copy. And also something that you guys just mentioned, right? Different layers, they have different optimization target. And sometimes those targets may be conflicting with each other. And from the performance perspective, or say a performance programmer's perspective, right? The biggest issue is that, okay, programmers are considering the rest of the computer system as a black box, and we don't want to know, and we don't think we need to know, right? So it turns out, again, I think that's one of the animation that I use a lot in my class, right? So sometimes you think your computer is probably as powerful as a Pikachu, right? So you think, okay, this is the best practice when I am programming. However, in fact, right, you are getting a completely different Pokemon, as you can imagine, right? And for this one, you probably want to use some kind of psychic attack instead of an electro type, right? So, but they all look similar, right? And if you have no knowledge about that, you keep asking this guy to do electro type, it's not going to do it well, right? So, so those are the problem with layering. And another one of the paper that try to tell you how serious this problem is actually one of the paper that's assigned in this lecture. Is actually Don't Stack Your Log on My Log. I really like this paper because it has a very interesting title. And so first of all, can anyone recall from your operating system class what is log? What is log? Not this guy, right? Log on log, right? Don't stack your log on my log. Do I mean to say this? No, right? What is log? Metadata, that's not log. Okay, so that's the good thing about logs, right? But what essentially a log is, right? So some of you have better mathematical background, you would think about log like this, right? That's the thing that I'm talking about. So what is log essentially? It's what? It's what? Say again? Short history of program execution. Okay, so why do you say it's a short history?
But like we don't keep all the details.
We don't keep all the detail? Okay, so that's a different kind of log, right? So when you say about this log, it's actually about like a debugging log or a system execution log, right? But okay, so that's another type of log. But when we generally say log, what does that mean? So it's one type of log, and it does have the property that I'm going to talk about. So what is log? Okay, so maybe I can put the question in this way. So for that type of log, can you think of a few properties of it? time, okay. And what else? Error number, what else? Okay. The log just save what?
Saves what the program did. Like,
save what the program did. Okay, so how it saves? In a queue, and then circular queue. Is this what a log is? It's just writing it to a log file and then saves it in storage, right? So that's a log that software will produce, right? And that kind of behavior is what we typically call log. So, okay, so in general, in computer science, when we talk about log, not talking about like logging, right? Not talking about the log file. When we talk about log in general, it means that we just keep producing result, or say we just keep aggregating stuff. That's a log. So can some of you try to like recall this on top of your head? What is a log structure file system?
So we log the writes.
What do you mean by log the writes?
We have, for example, we are working on a file. Each time we want to write some data to the file. And then instead of doing the writing, we just log the writes.
What do you mean by log the writes? Don't use the term to explain the term itself, right? So what's log the writes?
Copy it in memory, but not write it to storage.
That's not log. Okay, I think you guys, okay, so I feel we need to figure out how to improve our operating system education. But okay, let's talk about one of the significant example of log structure file system. So the idea of log, okay, so we are getting there. So the idea of log is basically saying you just append all the writes to the end of the log. And log is just like the current aggregation of your data or whatever, right? So what happened is that, right? So when we talk about log structure file system, you are treating the whole disk as a giant file, a log file, for example, right? And every time when I want to write something, I just append my data to the end of the log. And of course, you guys are talking about the optimization, right? So for example, what happened in log structure file system is that we create a write buffer in our system memory. And whenever I want to present the content in my write buffer to the disk, I append the data chunk that I want to write down at the end of the disk space that is currently allocated, right? So if I have another, and well, so for log structure file system, they put an inode at the end of each of the data chunk to ease for the log the lookup. However, right here, the main point is that the data chunk is written to the end of the log, which is considered as the end of the current allocated disk space, right? So now, if I have another data block that I want to write to the disk, based on the idea of log structure file system that I just talked about, based on the idea of logging that I just talked about, where should I put this data to? At the end of where? Like, okay, so from this place, right? Like, should I put it in the green part, the purple part, the beginning of the blue disk space, or the end of the blue disk space? Beginning of the free space, right? So I put it in the beginning of the free space, or say the end of the allocated space, right? So that's the log, right? So whenever I want to perform an update, everything is appended or aggregated into the end of the current file, or say the current log, right? Okay, so now you might want to ask me a question. What if I want to update data chunk 1 again? What happened, right? So in the design of logging in general, or log structure file system, what happened is that, again, I'm only updating stuff to the end of the log. So I still committed to the end of the log. But some of you might be asking, right? Then how do I know which version of the data chunk 1 should I be using? So the answer is that you just update your metadata at the very beginning and have it pointed to the new location, right? What? You have unnecessary data, I understand, right? But don't you feel like we have learned this before, even not in operating system? What was that? We have, where do you see this kind of concept before? Right, so we have duplicated data, but we just invalidate that, right? So it's still there, right? Okay, we can bring it there later, right? It's still there. You are right. It's still there. But didn't we see this kind of process before? Where is that? SSDs, right? And indeed, SSDs, they are updating their data or allocating their data in a way as a log. Okay, so why SSDs or our file system want to make themselves logs? What are the good things and bad things about logs? Can you, based on what you learned from this process, can you come up with a few good things and bad things about logs? 3 minutes. Grab a few friends.
There could be like a lot of updating that needs to happen. Yeah. So overhead. What's the other good thing? That's it. Yeah. Rights. Rights? What was the paper cup? I did it like 3 days ago. Well, this is this logging is. You're talking about the dose site. Yeah, the dose site. It's talking about like the SSDs and like your operating system and other processing top of the OS. Like they all keep their own logs, and then like those logs have their they each have their own so like suppose like under the database there's such like SSD controllers. Why? Where did you hear this from?
Yeah.
All right, good things and bad things about logs. When I tried to write this program, this problem, I was thinking about there is some kind of games that are typically played within couples, right? Like, can you say 5 good things about each other, right? I was thinking about like, oh, what's that game called? But I couldn't find an image of it. But anyway, so what are the pros and cons about logs? What are the good things about logs? And what are the potential bad things about logs? Like why both the file system and the SSD, they all embrace the idea about having logs? Performance, okay, in what way? Writes are fast. Okay, so for example, right? If I am for flash SSD, right? We learned before the reason why we want to use this kind of log update is just because instead of erasing the original location, right, which is taking a lot more time, right? If I use log, I just write to the end of the log, and that would save me a lot of time. Okay, that I accept. What else? So performance is one of the issues, right? But why file systems, they adopt the idea of logs as well? Version control. How is that achieved? Here's the thing, right? So some of you were saying about, okay, I create another like version of the code, the data, right? Isn't that like a garbage? But the thing is that, okay, if I want to find a previous version, actually logs help you, right? Actually, the logs helps you because I just figure out from the priority part of the log, can I find the version that I just updated from, right? So that's actually one of the good thing about log, right? And another good thing about log is that, okay, and that's probably another reason why operating system, or say in general file system, they adopt the idea of logs, is because computers, they are not stable. Agree? How many of you never experience a crash when you are using a computer? Right? Here's the thing, right? Every program has a bug, and sometimes the bug leads to crash, right? Like every computer crashes, right? So the thing is that crashes may occur, and when crash is going to occur, it's unpredictable. So we have to be well prepared for that, right? And in fact, the good thing about log structure file system or logs in general is that if the crash occurs, and if I'm currently updating data, right? And if you think about if I am updating the metadata, which is really important, right? And in the past, if I don't have logs, if the metadata is right, if I'm writing the metadata and right now it crashes, what happens? Everything is done. Everything is gone. Everything is gone, right? But if you have a log structure file system or a log, at least you can find the previous working version, right? Instead of trying to figure out how to recover the failure one, right? So that's another reason, like crash recovery. That's another reason why we love logs. And another thing, which is which is just like what you have seen, right? Because the log structure file system, you always append to the end of the log. So you are actually aggregating the data you are going to write in a chunk, as chunks. So it makes caching a lot easier, right? And it exploits the spatial locality when you are writing data, updating data. Therefore, that's why log is even better for performance, because you always have sequential update at the end, right? However, the bad thing about logs is garbage collection, right? As some of you just mentioned, okay, I create a lot of invalidated versions of my data. And once a while, I have to rearrange the live data that I have and erase old versions so that I can make up space for newer updates. Otherwise, one day, all my log structure, all the space that owned by this log structure file system or the SSD, well, even though like a lot of it are invalid data, I cannot do anything new, right? So that's the bad part about logs, is that you have to do garbage collection. Okay, so like here is an example. Like, okay, so for example, if I'm updating, right, if crash occurs in the middle, I can try to find an old version from the beginning, right? And if write failed, right, like, okay, I can still find a copy at some point, right? And so logs are everywhere, right? Because it's really a good idea. Logs are everywhere. So for example, last lecture we talked about database system, like and the format they use, right? And in fact, database system is an application, right? They also have a logs in their own, right? So this is what happened. Log is everywhere. So at the application level, the database system, they have their own log that tries to aggregate all the updates as a log, right? And they try to commit all the updates once. So you don't have to create a lot of fine-grained requests to your underlying system to minimize the overhead in software, right? So that's why database systems have a log. And when they commit a log, it's called a transaction, right? So that's what transaction-based data system looks like. So log is an essential part in database in general. File system, it also have a log, as I just said, right? SSD, they also have a log, right? So you have a lot of logs in your system, right? And as some of you just said, they can't interfere with each other. So let me give you this example. So saying that I have a file system, this is a log structure file system, right? So here I use this gray part to indicate this is an invalidate copy of the data. And this is like a free space of your data, right? And this is like from the operating system's file system perspective. And we mentioned SSD, they try to pretend themselves as a conventional disk. So they still expose the logic block address to the operating system. So from the operating system's perspective, they are thinking about, I have a serial space from 0 to the end. And the whole thing from LBA 0 to the LBA n-1 is considered as a single log, right? So they operate just like a single log. So if I have data that I need to update, right, then I just invalidate the older copies like this, right? And whenever I'm running out of LBAs, I will perform garbage collection, right? To this, you guys agree, right? And in the SSD level, okay, I received those logic block address. And as you guys learned before, SSDs has its own formula to perform updates and perform garbage collection accordingly, right? So for example, if I have a set of data and their current location is pretty much like this in the SSD. Okay, so let's run this a little bit. So now, at this point, my SSD feel like I don't have sufficient amount of space. So I want to do garbage collection. That's reasonable, right? So the SSD will figure out, okay, the best way to do garbage collection right now is probably get the ABF relocated so that I can reclaim the complete block 1. So I do this, right? And it sounds about right. And I erase my SSD block 1. So I have a lot of free space. Everything looks good so far, right? Okay, but here's the thing. Now, at a file system level, I figure out, okay, I also want to do garbage collection, right? So to do garbage collection, apparently, I should try to abandon this part so that I have consecutive LBAs to use, right? So I move the ABF to the end of the log, and I want to erase them, right? But what happens if I want to commit this update to the SSD? The links change? Is that simple? You cannot do this, right? What will happen is you would issue commands to erase the ABF and write ABF to a new location, right? So what happened is, okay, first of all, I update ABF with this new location. And then I invalidated the original location of ABF. Isn't that a bad thing, right? So I just copy ABF over. And the file system doesn't know this, right? And I write it again, right? So that's what's wrong with that, right? It's pretty much like this song, right? Scotty doesn't know, right? So here's the thing. We could have avoided this, right? If we can coordinate among them. So that's the main issue of layering, right? Because everyone has their own optimization locally, right? And this time, even though they have the same target, they want to perform garbage collection efficiently, they still contradict to each other, right? So that's the problem of layering, right? And typically, there is David Wheeler. He has a quote every software engineer would like to hear is that, okay, all problems in computer science can be solved by another level of indirection, right? That's actually one of the guidelines in software engineering. So that's why you see a lot of layering in software engineering. However, except for the problems of too many layers of indirection. And apparently, we are hitting that here. So if you have modern applications, so here's the thing, right? Like in database system, if what's typically happening right now is that, okay, I have database system manage a mapping table between my key value pairs and their location in the file. And I also have transaction support in my system, and I also have caching, I also have logs to check what are the updates, right? So that's the modern implementation of database system. So they have their own transaction, they have their own mapping tables, and they have their logs, right? So here, database system, they have their own mapping tables between key value pairs and the file location. And the file system has their own mapping table between the location and the a file and the LBA within a device. And the device themselves have an LBA to physical block address mapping. So every layer have their own mapping tables. And every layer also has a log, as we just said, right? So you can see every layer is doing replicating stuff. And the worst ever thing that could happen is just like the example that I gave you. They are actually leading to a lot of suboptimal performance case, right? So here's the thing, right? If you are aware your application is a database application that focuses on key value store, right? And if you are able to design or open up the device to the programmer or application designer, one potential thing that you can do is probably consider if I can make the whole disk like a key value store. Agree? Right? And you guys have learned in-storage processing, right? So you can probably imagine how are we going to make this happen, right? So, but here's the thing, right? If I imagine the whole disk could be considered as a key value store, right? And from your database applications perspective, what can I do? What should I do? If the whole disk is already a key value store, do you think I needed the mapping table? do I need a mapping table? Not really, right? I just pass the key to the disk and I can locate my data, right? I can get my data, right? If the whole disk is a key value store. Okay, do I need transactional support? Transaction support? Yes, but what if the key value store already did that? I don't need it, right? And the disk itself has a log. Do I still need logs? Probably not, right? So if your disk itself can be considered as a big key value store, you don't need mapping tables because you just use key to access the data you want, right? And you probably don't need transaction support because the disk itself is already a key value store, right? So it does the transactional support itself, right? Do you need logs? Don't forget, the SSD itself is already a log, right? So we don't need logs. So it turns out the only thing you might still need is the caching because we have to agree main memory is still way faster than your SSD, right? So it turns out if you look at this, if I can think differently by thinking about the application and system design without layering, this is what I could do, right? And I can greatly simplify my applications. And in fact, that would give you better performance, right? So like by doing this, right, because everyone writes to the same device, so there's not really a problem with data synchronization, right? But right now, if you are doing like concurrent database applications on a single machine with multi-threaded programming model, multi-programmed programming model, you will always have to think about how do I deal with locks, right? But here, everything is automatically serialized by your device internally, right? So you don't have to deal with that. And you don't have multiple interactions. You don't have multiple mapping tables. You don't have multiple locks, right? So remove duplicated optimizations as well. So it turns out this will give you better performance. So one of the paper that I and my colleague wrote in 2017 called Camel, and it's talking about how can we implement a high performance key value SSD. And the SSD itself provide a key value style interface using like set, get, delete, append, this kind of a key value store semantics as the interface between the SSD and the software. And it internally changed the flash translation layer to be something that's compatible with key value. And all you need to do is you just make the application directly talking with the device itself. And even though the file system, you can also make your file system live on top of a key value store. So for example, you can use your file name as a key, right? Or you can encrypt your file name as a key. And the data is just the value associated with that key, right? So actually, this is a very interesting idea, I think, I like, right? And in fact, it makes our layering a lot simpler and make the performance a lot better. So here are some implementation of Okay, so here's the implementation of our SSD, and here are some results from YCSB, which is one of the database transactional benchmark that that we used at that time. And you know, like, okay, so this is a relatively old paper, so that's at that time. Well, can you guess like why is this called YCSB? Where is the Y coming from? Like nowadays, right? If you see something start with a G, you must guess it's from Google. So this Y is actually from Yahoo. So Yahoo YCSB is actually Yahoo's benchmark of query processing, and it was actually a pretty good one. And so from this benchmark we see you can get like at least you won't have the performance in the worst case is about the same as without it. But in the best case, you can get like more than twice speed up with this kind of a single layer design, right? So you can see like without this layering, how much you can improve your performance. Okay, so that's one thing, one example that I try to tell you the good part about cross-layer design. So another use case about cross-layer design is actually approximate computing. So we have been talking about approximate computing, right? And can you tell who is this guy? Right? Okay, so if I only show you the right-hand side, can you tell who is this guy? Still the same person, right? But what's the difference between the left-hand side and the right-hand side? Resolution is worse, right? The right-hand side resolution is worse, right? But you can still see it, right? So you know approximate computing is working here, right? Because as long as you don't miss the key information, we are still able to see that happen, right? So that's the concept of approximate computing. And we also learned approximate computing a long time ago from one of the neural processing units in supporting general purpose approximate computing. Do you remember that paper? The MPU paper, right? So it's also the same, right? Like they try to see where in a program is it able to be using the concept of approximate computing. So for example, right, lower the resolution, I can still tell this is Mark Zuckerberg, right? So this is definitely part of the program that you can use for approximate computing. So I can train a neural network for that and give me the approximate result. So this is the concept of approximate computing. But remind yourself about this approximate computing and grab a few friends of you. Can you think of a few good things and bad things about approximate computing?
It's really good when you're not really like crazy about the precision. Yeah, exactly right. Yeah, it was like talking about whatever, like pseudocoded using like approximate computing. Really? It was one of them. It was CPU, right? Bad idea. But you do need like specialized. Yeah, that's okay. Then yeah, it was that one. Yeah, that's a good case to use. One of the bad ideas. So one of the cases where we need the exact result you're producing, something else kind of depends on the result that you're producing. Yeah, that's true. I didn't think about that. Yeah. And you can involve human lives. Yeah, I was about to say. Oh my god. Yeah, no, yeah, you could go that's crazy. That's so funny how you got that. Dude, yeah, like I said, I think it works. No, I ran into the same thing that you. Yeah, like before the errors. Okay, what I was trying to say is before the errors were like wanting to install this package. Where currently there's this package installed online. Yeah. But like now it's just saying like it doesn't exist. Period. That's because I like tried to like delete and reinstall a couple things, but just made it worse.
All right, so Good things about approximate computing, bad things about approximate computing. What do you guys think? Less storage. What else? Resource limitation. Talk about that. Precision loss and resource limitation. Can you? Storage? So what is good about? Is it good or bad? You won't need so much data. Okay, what else? You lose precision. You cannot use it for high precision tasks. Okay, so when I'm at storage, how do I know this data set is going to be used for applications cares about precisions or not? Can you make that assumption? No, right? If I'm a cloud vendor, I cannot make that assumption, right? So a lot of you were saying about I can save the storage. It doesn't really work out that way, right? But why? What other than that? What are the good thing about approximate computing? We don't need to have good algorithms. Okay, so you are talking about like a neural processing unit, right? You don't really need to spend time designing your algorithms. What else? So a few good things about approximate computing, right? So for example, the original reason why people want approximate computing is because you can make your circuit smaller, right? So for example, if I could use 16-bit computation instead of 32-bit, right? And if I am doing multiplication, I can save 75% of the area. Or on the other hand, within the same area, I can have 4 times more throughput, right? So you can either use this advantage to save the cost, reduce the money you spend, or spending the same money but get 4 times better performance, right? So either way is good, right? So also, if I want to perform some computation in a high precision way, or getting a very precise result, I might need to do a lot of very complex algorithm or complex optimization. But if I just allow to use approximate computing, right? For example, I can just use a neural network model to deal with it, right? And that's probably simpler than the original algorithm, right? Smaller data, as some of you said, right? So if I can reduce the precision of my data, I don't need to send out that data. Okay, but here's the thing, right? They also have bad things about it. For example, the result, and the result may be unsatisfying. And sometimes if the result is too bad, I have to recompute. So it turns out the performance will be worse because I have to recompute it, right? So also there aren't that many applications can use approximate computing. So again, right, one problem that I just mentioned is if I cannot make any assumption regarding what application that I am going to run this data set on, I cannot really store the data in lower precision, right? And if you cannot store the data in the lower precision, what is happening? So first of all, I still have to faithfully, okay, so maybe that's not the right one. Okay, here we go. Okay, so first of all, if I cannot assume I'm going to use approximate computing for my application, then the only thing I can do is to faithfully store the original resolution of my data, right? So what happened is that I still have to send out raw data. So here, for example, I'm sending out this high resolution bear. This is actually the Scottish bear of UCR, right? And you can see this part is actually Scotland. Okay, Scotland. Okay. So this is the raw data, right? This is the raw data you have to send out because that's where we have what we have in the storage. And then if I really want to take advantage of reduced precision and reduce data amount, the only place that I can make that happen is that, okay, I try to lower the resolution at the CPU level before I send it out to the GPU, right? And GPU can operate on reduced precision data, right? So that's the only way I can take advantage of that part, right? But from this part, which is actually more of a bottleneck if you send out the raw data because this link is slower, right? So again, another thing that, and also like, okay, another thing that we have to do is the quality control, right? For example, in your application somewhere, you have to decide if the quality is too bad, right? If the quality is too bad, we have to reject the result and redo it, right? So those are the general process of doing approximate computing nowadays. However, right, you can see you still cannot optimize the link between the storage and the system main memory, right? So another paper, okay, today I feel like I'm always doing an advertisement, right? So another paper that we wrote in 2019, right, is called varifocal storage. So here's our idea. So, and we call this a holistic system architecture in a way that we let the storage device know what kind of computation, or say, if this is an approximate computation program, right? So if this program, or say this application, use the concept of approximate computation, computing, tell us how good the resolution you want from your data, right? So it turns out what we can do, right? So we call this varifocal storage because we are actually changing the focus of your lens, right? You can consider the varifocal storage. It has a camera, and depending on how good you want to zoom in on your data, we give you that resolution you want, right? So if I just want a raw resolution data, right? The raw data is retrieved between the flash chip and the flash controller. And we adjust the data resolution within the SSD itself, use the near data processing concept, right? And then quality control, we also can do some of the quality control in the SSD, right? And so that's our approach. So some of the interesting stuff that we can talk about, right? So for example, the concept of varifocal storage is pretty much like this. So instead of just saying that I want to read a data, you can pass an additional argument saying that what's the resolution I want, right? So for example, here I say I only want 25% of the data precision, right? And so that you can just get a smaller size of data. And we use our algorithm to downsample the data set. And so with that, right, the original resolution Mark Zuckerberg is shrink to one of the 25%, right? One. And then we send the 25% out. So you can imagine we can reduce like 75% of the traffic, right? And everything else is still the same, right? So that's the basic concept of it, right? And here is talking about how we extend our system and what do you need to do. And another thing that in our work was talking about, again, this can only be done if you have a cross-layer design approach, right? So another thing we have been thinking about is that, okay, one of the reasons why approximate computing is typically fail is because when you adjust the resolution, you just make it look too bad, right? And instead of setting that, okay, so here's the thing, right? You, as the storage device, we could have done some quality control of that. So if we have already know that data is too bad, just don't send that out, right? So sometimes I do like to say this to my student, right? So for example, every time before the paper deadline, I feel like, okay, if you know that paper you are written is not great, just don't send it to me, right? You know what I'm going to say, right? So here's the thing, right? So our idea is that inside a storage device, right, we check some of the key features of the downsized data. And if the data is, so the traditional approach is, okay, we just send a low resolution data out. And if the data turns out yielding a very bad result, right, the whole system would tell us, okay, let's redo it. That's the conventional approach. But our approach is different. Is we believe garbage in, garbage out, right? So for example, like, okay, if people working with you just keep giving you some garbage data, right? You will always get garbage out, right? So our idea is also about the same. Is that okay? Even though the application requests like 25% resolution, as our end, we do our own quality control to see this 25% already lose a lot of key features of the data set. So for example, if 25% is far off from the original data set, we just reject it and tell the application, we are not going to send this to you because it's not going to work, right? So you can avoid a lot of recomputation. You can avoid a lot of inefficient data exchanges, right? So that's another example of cross-layer design. And of course, we have quite a few mechanisms to sampling the data and figuring out if we are losing the key features. However, this is just another example telling you why cross-layer design is important nowadays. It's because right now we make our systems so complicated in a way that we have too many layers. And because each layer is trying to filter out some of the information, and they try to keep things simple. But the thing is that they also make themselves a black box. Didn't tell you the information that you need. So it turns out we will lead to suboptimal optimization, or we are making the result worse, right? So for example, the original purpose of approximate computing is to improve performance. However, without cross-layer design, you are actually going to not taking full advantage of this and making the performance worse. All right, so this concludes what I want to talk about today. And quick announcement. So we have final project presentation on March 21st. And please book your order. Well, everybody is going to present on the same day, right? So please book the presentation order from the shared calendar. And because it's close to the lunch time, right? So we are going to do lunch. Okay, that's the most important thing, right? So also prepare your stomach to have pizza provided. And again, there's no next lecture next Tuesday because sorry about that, because I have some other duties that I committed on that day. Originally, I'm going to be a general. I'm going to fulfill my general chair duty at San Diego for the non-volatile memory workshop, but there are something that UCR want me to do on that day as well. So I cannot teach on that day, but we will be back on next Thursday. All right. So if anyone else, if you don't have any other question, enjoy the rest of your week. I will see you again next Thursday. And I know it's close to time about the final presentation. So if you have any question, feel free to send me an email and we can see if we need to meet. All right. Other than that, enjoy the rest of your day, rest of your week. I will see you next week.